Inside an electric arc furnace, steel is made through brute force. Massive electrical current is driven directly into a pile of jagged scrap metal, creating a contained lightning storm that melts steel at over 3,000 degrees Fahrenheit. Keeping that storm burning is expensive. Between the initial melt in the arc furnace and the subsequent chemistry adjustments in the ladle refining furnace, you are looking at 70% of a steel mill's total conversion costs. This chart shows the energy gap in those operations. The best-in-class furnaces consume 300 kilowatt-hours per ton of steel, but the average furnace consumes closer to 380. Across an annual production of 500,000 tons, that 80 kilowatt-hour difference translates to $2.8 million in wasted electricity. This waste occurs because most melt shops run static, fixed-power programs. They apply the exact same electrical recipe to every single batch of steel, but every batch, or heat, is unique. The scrap metal loaded into the crucible varies in density, moisture content, and chemical makeup. Human operators must manage this volatile process from heavy industrial walkways directly adjacent to the heat. They attempt to monitor a reaction they cannot safely see. By applying a rigid process to a volatile thermodynamic system, modern melt shops bleed millions in capital every year. Electricity is only one part of the equation. To deliver that electrical current into the scrap, the furnace uses massive columns of compressed carbon called graphite electrodes. These electrodes are consumed during the melting process. Replacing them accounts for 10 to 20% of the total conversion cost in an electric arc furnace. This diagram shows how graphite is destroyed. First, tip sublimation. The arc's heat vaporizes solid graphite at the electrode's tip. Second, sidewall oxidation eats away the surface. Ambient heat and chemical exposure continuously erode the column's sides inward. Operators traditionally mitigate this wear through manual observation, but the scale and opacity of the heavy steel furnace shell make it impossible to see the active arc or adjust the columns in time. This creates an entrenched industry dynamic. Graphite manufacturers profit from this accelerated consumption. They have a financial incentive for the bottleneck to remain hidden. The cost of electric steelmaking is the rapid, invisible destruction of the tools required to deliver the energy. Optimizing an environment requires measuring it, but the electric arc furnace destroys standard measurement tools. The crucible presents two threats: extreme physical heat and severe electromagnetic interference. If you introduce a standard steel probe anywhere near the active arc, the tip blisters and physically warps. Even if a probe survives the heat, the intense electromagnetic field corrupts whatever data it captures. The telemetry becomes useless. Without real-time internal data, operators rely on delayed impedance metrics. They blindly position the hydraulic mast that holds the electrodes. This instability accelerates graphite wear and wastes energy. The arc flares unpredictably because the adjustments are reactive. The steel industry faces a hardware constraint. The system remains inefficient because the environment neutralizes the instruments designed to monitor it. The solution requires a workaround. If you cannot place a sensor inside the lightning storm, you must measure the thunder from the outside. Instead of placing probes inside the crucible, engineers install an industrial acoustic sensor array. They mount it behind a heavy concrete blast wall. From this safe distance, the array records the specific audio signatures emitted as the scrap metal melts. Deep learning models then process these massive audio datasets. This logic model shows the correlation. The AI maps specific acoustic frequency shifts to post-heat physical measurements of graphite electrodes. Direct trend lines connect specific sound spikes to physical wear events. This builds a baseline predictive wear model immune to electromagnetic interference. Acoustic data models bypass the physical limits of the furnace. They capture the operational control point from the consumable suppliers. This timeline illustrates the 4 phases of a furnace heat: boring, meltdown, flat bath, and tapping. Flat bath is the zone of maximum waste. Scrap is completely melted, but energy is still poured in, costing $40 to $60 a minute without adding value. The acoustic model listens for the exact moment the meltdown is complete. It then dictates the physical descent and voltage of the hydraulic mast. Adjusting the arc length dynamically based on real-time sound reduces electrode wear by 15% on every heat. Optimizing the arc furnace alone is a mistake. Efficiency depends on the chemistry requirements downstream at the ladle furnace. In the ladle furnace, operators have historically relied on manual calculations. Miscalculations lead to expensive overalloying or off-spec heats. AI models now calculate automated alloy dosing. They combine live spectrometer data with recovery models to remove the guesswork. True optimization requires a connected intelligence that manages data from the arc furnace mast to the final ladle chemistry targets. The final result is a closed-loop system. It integrates acoustic signatures and process data to drive mechanical actuators. Long short-term memory neural networks use this telemetry to predict the thermal evolution of every heat. This modeling allows operators to hit ladle furnace endpoint temperatures within 5 degrees Celsius 89% of the time. This precision extends to maintenance. Tracking thermocouple trends via AI prevents catastrophic failures of the heat-resistant bricks lining the vessels. This intervention extends the refractory campaign life by 25%. It reduces total unplanned downtime by 40%. These systems represent a practice of restorative engineering. Automation's highest purpose here is removing human operators from hazard zones. It relocates them to clean, remote control rooms. Safety and operational clarity replace the inherent fear of the factory floor. Capturing and decoding the proxy signal allows steel mills to permanently shift their per-ton cost basis. Real technology restores human capability. It converts blind, dangerous environments into predictable, controllable assets.